Welcome back. So last time we proved the continuity of addition as a map from C cross C to C. We did this because we boiled down the limit laws to the essential characteristic of these arithmetic operations that they should be continuous. So we have a previous result that says, so long as this operation is continuous, then this limit law will work. But that leaves us with the work of proving that these operations are continuous. We proved that plus is continuous, and I kind of wave my hands at the fact that minus is continuous, which is easy and the same. Next, we're going to try to prove that multiplication is a continuous operation from C cross C to C so that we can end up with a limit law like this. So the statement is that multiplication is a continuous operation. What does this mean? It means, let's say we have A, B, and C, and we let C be their product. Then continuity of multiplication means for every epsilon you like, there is a value of delta 1 and another value of delta 2, so that for any A and X and Y in the complex numbers, if X is very close to A, proximity less than delta 1, and Y is very close to B with proximity less than delta 2, then the product XY is going to be very close to the product AB, and the proximity will be less than epsilon. So the natural proof structure here is to let epsilon be arbitrary and then immediately choose the values of delta 1 and delta 2, right? Because that's how this statement is structured, and the proof should follow that. That's kind of idealistic. It's very hard to immediately know the values of delta 1 and delta 2 without doing a whole bunch of computations about this term. So what we're actually going to do is we're going to choose epsilon, and then we're going to say, okay, later the rest of this is going to happen, but what we really need to do is compute and control this term. So that's what we're going to do. So, so let epsilon, so this is the proof, of course. We're going to begin by letting epsilon be an arbitrary positive number. And then we're going to choose, I'm just going to sort of mock up that we need to choose delta 1 and delta 2, but we as yet have no idea how to choose them. Nevertheless, we should say that X and Y are going to be arbitrary, and we're going to assume these things. So, so we're going to let X and Y be in C, and we're going to assume that the distance between X and A is less than delta 1, and we're going to assume that the distance between Y and B is less than delta 2, because that's necessary there. And then the important thing to do is to prove this. Now, this is going to lead us into the weeds with algebra, and so we're just going to sort of have some patience with this term, and we're going to see what happens. We're going to follow our nose and see what happens to this term as we expand it. So xy minus ab absolute value. So I should maybe say then absolute value. So basically, I want to do manipulations to this term, and I want to get it eventually to be less than epsilon here. So how are we going to do that? Well, I don't know what we're going to do. This is a difference of two products, and there's no nice algebra that allows us to separate. I mean, wouldn't it be nice if xy minus ab were equal to x minus a times y minus b, and then we would get terms like x minus a and y minus b, and we would be able to control the term. But that's not algebraically correct, right? So we need to do something which is algebraically sensible here. If it were xy minus ay, then we'd be able to factor out the y. If it were xy minus xb, then we'd be able to factor out the x. So if the terms were even a little bit mixed, we'd be able to factor things out productively. And when we factor out, like if it were xy minus xb, for example, if we factored out the x, notice we would have a y minus b. And that would be a really good term to have because we have control over that term. So we kind of wish that we could factor something out here. And that's going to motivate our next step. The next step is going to be we're going to add and subtract a term in the middle that will allow us to split this thing in an interesting way and factor pieces out of each part. So let me illustrate. So what we're going to do is we're going to take xy, this term unchanged. We're going to subtract xb, and then we're going to add xb. And let nobody argue that this is algebraically invalid, right? I've subtracted something and I've added something, and it's the same thing. And it may be a little bit magical, but hopefully I've motivated a little bit by saying, look, we want to be able to factor things out of this and factor things out of this. And notice that from these two terms, a b will factor. From these two terms, an x will factor. So that's interesting. So this might help. Now notice that we have an absolute value of a whole bunch of terms, and we're going to apply the triangle inequality in an effort to control it. So here we get the absolute value of xy minus xb, and then plus the absolute value of xb minus ab. So this is certainly a lot more complicated than what we started with, but it is an improvement in some way because this is now sort of mixed up so that we can factor out an x, and this is a little bit mixed so that we can factor out a b. And that's probably good. So that's what we're going to do next. We're going to factor an x out of this and a b out of this, and then we're going to see what happens. So this is going to be equal to, of course, when you factor out the x, it's still within an absolute value. And so I probably have been saying absolute value too much. It's actually modulus, but you get what I mean. So we're going to factor out modulus x and then y minus b. And here we're going to factor out a b. So this is going to be x minus a, and we'll factor out a b, and it's still within the modulus. So maybe I put a dot in here to make it more clear that I'm multiplying. So that's actually good because y minus b is something that we've assumed control over, although we haven't actually specified yet what kind of control we have over it because we don't know yet what kind of control we need. But in theory, when we get to the proof here, knowing the value of delta 2, then we have control over the y minus b term, and we also have the same kind of control over the x minus a term. So let's actually assert that that control is happening here. This modulus y minus b is less than delta 2, so let's fill that in here. So we get modulus x times, and then that's delta 2. Notice here that modulus x is positive or 0, and so replacing this with this really is the inequality which goes in this direction and not the other direction, right? If x were a negative, then replacing this with a greater thing would cause the inequality to flop, but I know that this is a non-negative value, and I know that this is a non-negative value too. So that's modulus x times delta 2, and then this thing is bounded above by delta 1, and so that's delta 1 times, and then that's modulus b, which of course is also a non-negative value. So that gives us this. Now, that's actually, so this looks symmetrical. It looks like we kind of have equal control here as here. Like we should do something here and we should do the same thing here. But it's not really quite so simple because the structure of this proof means that these terms have to be dealt with in different ways. And let me explain. So the theorem statement itself begins, let A be in the complex numbers. A and B are fixed given numbers. They're certain numbers, right? Then our proof continues, let epsilon, choose delta 1, choose delta 2, right? Delta 1 and delta 2 are these fixed numbers, whatever we've chosen them to be, they will be. Now, we have to choose, now after that, we say let x be in the complex numbers. Now, ultimately here, I'm going to have to eventually fill in the values of delta 1 and delta 2. And I'm going to have to say, well, choose this magic number here and choose this magic number here. But when I make those choices, I will have to write them here in the proof. And their location here corresponds to the fact that they have to exist. They can depend on epsilon, but they cannot depend on x and y, right? So if I write let delta 1 be 1 over b, for example, then that's perfectly fine because b is determined up here. But if I say let delta 1 be 1 over x, that's never going to fly because x is decided after delta 1 is chosen. And so the asymmetry between these terms is actually a really important point. This term is going to inform what choices we need to make about delta 1. And we might like to choose delta 1 to be, for example, epsilon over 2 divided by modulus of b. And that would actually work just fine. And we would control this whole thing with, and the whole thing would be bounded by epsilon over 2. If we want to choose delta 2 to be, for example, epsilon over 2 divided by modulus x, so that these will cancel and we'll get an epsilon over 2 here, that is not going to fly because delta 2 cannot depend on x. It needs to be chosen before x. And for that reason, I'm going to continue modifying this term so that I compare it to A more productively and compare it to things that I can make delta 2 depend upon. And so with that in mind, I'm going to actually subtract and add the value A from this modulus in here. So let's see how that's going to work. That's going to be the modulus of x minus A plus A delta 2 plus, and then I'm copying the other term, delta 1 modulus B. So this might seem like a little bit crazy here, but I'm comparing x to A once more, and then I'm going to split this again using the triangle inequality. So that's going to be, again, less than or equal to modulus x minus A times delta 2 plus modulus A times delta 2 plus delta 1 times modulus B. All right, now we're getting there. Now again, so compare this to what we had before. Before we had a delta 2 multiplying the x, but the x was kind of a confusing thing because delta 2 cannot depend upon x. So we had this kind of situation before. Now we have a modulus a times the delta 2, and then we have this extra term that we have to control again. But notice that x minus a is assumed less than delta 1, so I can say that this term is less than or equal to delta 1, delta 2, and that's what we're going to do next. So this is going to be equal to less than, this is going to be less than or equal to, well, it's going to be strictly less than, I suppose. So strictly less than delta 1, delta 2. So here I'm replacing this with a delta 1, which is greater. And that's delta 2 plus modulus A delta 2 plus modulus B delta 1. And this is more complicated than what we had before. But the nice thing about this quantity is that it has no dependence whatsoever on x or y. It depends only on a and b, on which, which are decided at the beginning of the problem. And it depends, of course, on delta 1 and delta 2. Now, what are we trying to do again? Let's try to remember. We're trying to let epsilon be a positive number, and then we're trying to make strategic choices of delta 1 and delta 2 so that whenever x and y obey these inequalities, then xy minus ab will be less than epsilon. So ultimately, we've simplified, well, we've modified our formula so that it looks like this, and we have to still end with a less than epsilon somehow. How are we going to do that? We're going to control each of these terms. And ideally here, we're going to try to force each of these terms to be less than or equal to epsilon over 3. So we have 3 terms. None of them can be negative, so we're going to try to bound each one with epsilon over 3 and add them up. We still have our choices of delta 1 and delta 2 to make, and we're going to make them in such a way that we force each of these terms to be less than or equal to epsilon over 3. So how are we going to do that? So it's actually a little bit dicey because in order to control this term, we have to simultaneously control delta 1 and delta 2. In order to control this term, we have to control delta 1 in terms of b, and this one we have to control delta 2 in terms of a. So we have like several requirements to juggle, and we're going to make them one at a time in a slightly asymmetrical way. I wish there was like a nice, clean, symmetrical way to make all these things satisfied at the same time, but that's not exactly what we're going to do. So we're going to choose delta 1 first, and we're going to choose it so that this term is less than or equal to epsilon over 3. So actually, we're going to choose it so that this term is equal to epsilon over 3. So let's talk about how to choose delta 1. So this is actually, technically, this is logic that goes in here, but I haven't left myself enough space to fill it in. So we're going to choose delta 1. And what are we going to choose it to be? We're going to choose it to be epsilon over the modulus of b times 3. Okay? Super simple trick, so that when we multiply it by modulus of b, we're going to get epsilon over 3. Technically, there is something we need to worry about here because b is an arbitrary complex number. It could, in theory, be 0, in which case its modulus would be 0, and then that wouldn't work. Now, if b is 0, then I have no concerns that this term is going to be large. If b is 0, this term will be 0 no matter what I choose delta 1 to be. So I don't really worry about this, but it means this formula is not right. So or 1 if modulus b equals 0. So basically, this is a bailout case. If modulus b goes wrong, so that this thing doesn't exist, then just choose delta 1 to be 1 because I don't care what delta 1 is. And one way or another, this term will be less than this. So then I want to just deduce here, modulus b times delta 1 is less than or equal to epsilon over 3. I say less than or equal to. If this is the choice we made, it'll be equal to epsilon over 3. If this is the choice that we made, then it'll be 0 itself. So that's less than or equal to epsilon over 3. Now I need to choose delta 2. Well, I can do the same thing to control delta 2, but then I lose control over the product delta 1, delta 2. So let's deal with these like in separate cases. So if I choose delta 2 to be epsilon over modulus a times 3, if I choose it this way, and then, or 1, if modulus a should happen, unluckily, to be 0, if I choose it this way, then modulus a times delta 1 is going to be less than or equal to epsilon over 3 for exactly the same reason that we controlled the first term here. Okay, so if I choose delta 2 this way, then, well, I will get control over this term, and this will be less than or equal to epsilon over 3. But then I will lose control over this term because I don't know what will happen when I multiply this by this, and I don't know whether that product will be less than epsilon over 3. It'll be something like epsilon squared over the product of these moduli times 9, and I don't know how to bound that, right? So that's, well, I mean, there are things you could do, but I don't want to. The simpler thing to do is to choose delta 2 again, which is not quite legal, but we'll fix it in a minute. If delta 2 is chosen to simply be epsilon over delta 1 times 3, notice that delta 1 cannot be 0. So I don't need any bailout condition here. Delta 1 is either going to be this positive number, or it's going to be 1, which is a positive number. So one way or another, this will actually be a positive number. So if I choose delta 2 this way instead of this way, then no, that's not the right condition. Then delta 1, delta 2 is going to be less than or equal to, it'll actually be equal to epsilon over 3. So this is kind of like, well, we're almost there. I figured out how to choose delta 1 so that I get control over this term, exactly the control that I need. I'll get that term less than or equal to epsilon over 3. I figured out how to choose delta 2 so that I can control this term to be less than or equal to epsilon over 3. I figured out a completely different way to control delta 2 so that this term will be less than epsilon over 3. So which choice can we make for delta 2? Well, we have to somehow make both of these choices. And that might sound impossible, but we can do the next best thing. We can choose the minimum of these choices. And if delta 2 is the minimum of these two choices, then we will satisfy both of these conditions, right? Whatever one is lesser, you choose that one, and then the other condition will just automatically be satisfied. Notice that this choice actually makes delta 2 depend on delta 1, which is legal within the proof so long as we choose delta 1 first. So it actually, in this proof structure here, it actually matters that I'm choosing delta 1 before delta 2 because delta 2 is chosen to depend on it. So this tells me how to choose delta 1 and delta 2. I'm not going to write the bailout conditions here, but the basic idea here is we choose epsilon over modulus b times 3 here for delta 1. And then for delta 2, we choose delta 2 to simply be the min of the two values, epsilon over the modulus of a times 3, or epsilon over delta 1 times 3. We choose it to be whichever is smaller. And once it's the smaller of those two, then all of these conditions will be simultaneously satisfied. And this thing will get to be less than or equal to epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is equal to epsilon. Now, technically, I'm supposed to have a strict less than epsilon here, but I've got one strict inequality here. So you chain these together, and because of that one, well, and also this one, then we get a strict inequality, which is the assertion finally that we need, which is that xy minus ab modulus is less than epsilon, and that's what we were trying to show. So this demonstrates the multiplication from C cross C to C is a continuous operation on complex numbers.